Okay, hope everybody had a good fall break. And this week we are going to introduce a new algorithm that's K nearest neighbor. And this also for classification mostly. I believe it's very easy to understand. So the concept of this algorithm is to find the nearest neighbors of this points. And if the neighbors are green, okay, then this point is classified as green. If the neighbors are, most of the neighbors are red, then this dot is classified as red. So, and how does it, and so all the features in the data, all the features in the data, they are represented as the points on a map, on a coordinate system. Okay. So if it's if this data only has two features, okay, then we use XY to represent it. xy to represent it. And if it has 3 features, okay, you have add another dimensional to represent the 3rd feature. And likewise, you can add a dimension to the coordinate system. And so how do we identify the neighbors? There are a lot of dots here. Triangle, a circle. How do we get this here? Okay. How do we identify which one is its neighbors? We calculate the distance between this dots and the other dots here. And if the distance is smallest, okay, these are its neighbors. These are its neighbors. Straight enough. And how we calculate the distance? See that we have the formula. You can. There are 2 systems, two ways to calculate the distance. And the common way they use is called the Euclidean distance. That is calculated by the direct distance. So it's x squared plus y squared, and then it's the square root of the it's the square root of x squared and the y squared. Right? That's a Euclidean distance, and there's another system called the Manhattan distance. That calculates the x plus y. That's a distance for these 2 dots. This one is most commonly used. So now we got its distance to its neighbors. If the k, we said k nearest neighbors, that means that we identify this, we classify this according to its k neighbors. If k is 3, okay, we classify it, according its nearest 3 neighbors. So if we classify it with its nearest 3 neighbors, what this star should be? What is the star should be? These are the 3, right? 3 nearest neighbors. And what is the majority of its neighbor? Triangle. So this one should be, this new instance should be triangle. Okay. And then if it's the k changes, or the result change, so the k changes. For example, the k is changed to 4. K is changed to 4. Then as a 2 circle and 2 triangle. Now we cannot decide what is shape. Okay, that's one rule when you decide the k value. So the k value should not be, if there are 2 classes, the k value should not be even numbers. It should not be 4. If it has a tie here, you cannot decide. Or if it has 6, it could be 3 to 3. You cannot decide. But when you select the k values, it will be better to skip those even numbers. And same if there are 3 classes. Let's add a square. If it has 3 classes, then the k value should not be 3 and 6. 6. If it has 6, it has 2 of each. You cannot decide either. So it should not be 3, 6, and 9. There will be a tie there. You can, they cannot decide the k value. Of course, if you give the 3 to the algorithm, it will still compute. Okay, I think that's how this algorithm works. So it's very easy to understand. It's really easy to understand. Next question. So when we are talking about the distance, we are talking about the numerical values, right? Distance, okay, numerical values, okay. X, Y are numerical values. So can we use this algorithm for categorical values? Oh, some article will tell you it can. Some articles tells you no, it cannot handle. I will say, my opinion, it's not ideal for categorical values, categorical variables. So technically, if you add another dimension like this, z could be, okay, 2 values, 0 and 1, okay, 0 and 1, and then add another dimension to it. It will still give you a number and plus z. Okay, so this will be changed to x plus y plus z. They could be 0 and 1. And because these are numerical values, these are quite different from each other. So adding this z, it still gives you a number that is distinguishable, unique. But for example, if we get features like a data with 2 features and 2 categorical variables, these are three classes for x, okay. So, 3 unique values for x, and y has 2 unique values, 1 and 2. So, hey, this is the instance here, and this is the instance here. So they would all overlap with each other. And if you got another instance, okay, this instance is what I want to predict. I'll give a good example. Add more distance, more instance. Okay, here it goes to our data. So these are categorical data. It's 3 variables, 3 unique values and 2 unique values on y. And I have a new instance here. New instance here. So I want to predict this, and if we select k equals k equals 3. K equals 3. Okay, whatever k equals 3. Okay. K equals 3. Then this one should be, and then 3, there are a couple of them the same distance. So you couldn't even identify which are the 3 nearest neighbors, really. You want to select 3 neighbors, and then all these are same distance to it. So the values are really not unique. So I want to say it's not ideal for data with a lot of categorical variable. But if we mixed with like numerical values, okay, if you add 0 or 1, it changed this distance. This distance of the sum changed, but it should still be unique value. Okay, let's walk through an example and see how this algorithm really works. Here I've already loaded the data and loaded everything. Okay. Yeah, I loaded the data. So this is a data set, a very popular data set to predict whether this flower is one of the 3 species. Maybe one of the 3 species. It's not said. But the target variable is a categorical variable. It has 0, 1, 2. It is to predict the species of the flower, and with this sepal length white and petal length and white. Okay, I got the data ready, and the first one we usually do is to see how many null values it has, and what else we usually see whether the data is balanced. Right? So I already checked it. This data here has no null values, so we can proceed. And the first one we do is to do EDA to see the data overview of the data and see how the features are distributed. So if we look at this histogram, what it tells us, what information we want to get from this histogram. Usually what information we want to get from the histogram, what we're looking to when you see the histogram. Like the behavior of the data. Well, like the behavior of the data, like where the mean is and then the yes. Yeah, we can see that. So these distributions look good. You can see they have a good variance in each feature. If the data is all the same value, it doesn't help to predict anything. So we should drop the feature, right? And these all have good variance. What else we can get from this histogram? Target variable. It's important. Target variable is balanced. It's a training data set, so they make it in a good shape. But usually what you got is an imbalanced data set. So that's what we're looking to in a histogram. And next, since these are all numerical variables, so what we like to do is to pull up box plots and to see whether there's a significant difference of the target variable and the numerical variable. Significance between the different groups of the target variable. So what does this box plot tell us?
Because like
Uh-huh.
the difference between the different groups.
Yes, they all have good difference between these groups for each variable, right? That's cool. And see which one has the most variance, the most significant variance between the groups. Yes, petal one. So this should be the ideal variable to predict. And this, if you see this, only have a little overlap between these two whispers. If it has no overlap between the whispers, okay, we just use this variable to predict the target. But it has a little bit of overlap between these two whispers. And if you look closer, you will see, compare these two graphs, what we found. They are almost, yeah, pretty close.
Yeah.
Exactly the same shape. That means this changes are the same as this one. They have a correlation, high correlation coefficient. They could have high correlation coefficient. So maybe you just choose one of them. And then you use ANOVA and the ANOVA and the correlation coefficient to test your observations. Or you pull up the ANOVA test, it shows okay, for all these features, the p-value is to 0, equals 0. So all these 4 features, they have this significant difference between the groups, 3 groups. So we can choose all of the 4 features. However, we pull up this correlation coefficient. You see, there are numbers close to 1. Close to 1. Let's just ignore this target. Okay, it's not this target variable. So we are looking into these numerical features. So, for example, petal width and petal length have correlation almost close to 1. Also, like a petal length and the sepal length, that's also close to 9. So, in my report, I chose this petal width because it has the highest F score, and then I didn't choose the white because it has a high correlation, and also length has a high correlation with the sepal length, so I didn't choose this either. I chose the petal length and the sepal width as the predictors. You can change the predictors and to see which one gives you the highest accuracy score. So in this in my report, I chose these 2. Okay, sepal, petal length. It gives me the highest F score, and also I chose sepal width because it has a smaller correlation with this variable petal length. So okay, so I fetch this data, fetch these 2 columns, and then the next step we are going to do is a new concept to you called feature scaling. Let's look back at this box plot or this histogram. If you see the petal length and the sepal width, these are the 2 variables we chose, right? So the petal length is the range for the petal length is from 0 to this actually 8, from 0 to 8. And the steeple wise goes from 0 to 4. They're close to each other. Okay, but if we goes to an extreme case, like the petal, so if we go to an extreme case, and this is the petal length, and then this is the sepal wide. Okay, and this could be 0 to 50. The numbers range from 0 to 50. So the length, okay, sometimes the length is usually longer. Okay, sometimes it could be the length range from 0 to 50, but the actual wide, the wide actually range from 0 to 10. So what could be that problem? See this one, create dot. So if you look at this picture, okay, and we have a new instance here. New instance here I want to predict. So this petal length goes from 0 to 50 as a good spread on this x-axis. This one, this W wide, it goes only from 0 to 10. Or even 0 to 4, so they are very close to each other. So the problem will be when we calculate the distance. When we calculate the distance, this distance is largely decided by which value? This distance is largely decided by the value of the x-axis. This y-axis has a little influence to this. Does that make sense? So this varies not, and then the y value has a smaller influence on the distances. But they are we are assuming they are all equal variables. So we didn't put any weight on these features. They should have a same weight, same influence on the distance. So what we are going to do is to change them into the same range. So this one goes from 0 to 50, and this one should be added the same number, so the times the same number, so the enlarge this y-axis, so these can also be on the same these can also have the same influence on the distance. Okay, so this is the now if we calculate the distance again, then this one, now the xy will have a equal influence on the distance, on the final value of the distance. So that's called a feature scaling. Do you understand that? Yeah. So the next thing is then how do we do the feature scaling? So these two pictures also shows the importance of feature scaling. You see, in this picture, that's the x1, this dimension, they are all on the same value of 0, on the same value of x1. So this dimension has no influence on the distance. Right? Instead of using this picture, we enlarge these distances. These distances are very small, right? These distances on the x-axis are very small. So we want to enlarge them and change it to this picture. Enlarge this distance on the x-axis. So if the picture would look like this. Now both dimension has a good influence on the distance. So that's called the feature scaling. And what it does is there are two methods for feature scaling. One is called normalization, and second one is called standardization. Right? Normalization, what formula for normalization is x minus the x mean and divided by x max to x mean. X mean. So this value will range from 0 to 1. You see, x max to x mean, that's the longest distance on the x-axis, right? And this value must be smaller than this one. So it will range from 0 to 1. Are we okay here? Yeah. So if we change this, so this is the x mean here. So this is the x mean here, and this is the x max is here. So the value for this one is the distance of this divided by this. So here the values goes 0, and those dots close to here. Okay, if this largest one, the max value, and this goes to 1. So that's a normalization. And if we use the standardization, then the formula is x minus x mean, the average number, the mean number for the variable, and then divided by the standard deviation. Okay. This doesn't range from 0 to 1. So usually for a features for the k nearest neighbor, we want it to be in the same range, 0 to 1. So we use a normalization more often. In some report, you will see they use a standardization. That's called a feature scaling. But it's supposed to improve the accuracy of the algorithm. And if you look over some articles, they will suggest you use a feature scaling for most of the algorithm, like logistic regression or linear regression. So it helps the algorithm to calculate the values. But I don't think, I don't quite agree with that. And you can try before feature scaling or after feature scaling, which accuracy is higher. You can try that. Some reports that, or in some cases, it doesn't improve the accuracy. So I wouldn't require feature scaling for all the algorithms, but for this k nearest neighbor, obviously this is an important step. Okay. Next, we can just build this classifier like we did for the regression. Like we did for linear regression or any of the regression. So here I used this method min max. We mentioned that that's for normalization. So you minus the mean value and then divide by the x max minus x mean. And if we look at this result after the normalization, we see the values are all from 0 to 1 now. 0 minimum and 1 is the maximum. So next, okay, I think that's all we need to do with data cleaning here. We are ready to build the k-nearest model. So we just import this method, k-nearest classifier, k-neighbors classifier, and then give its name, classifier or model 1 or whatever, and then use that data to train it. Use this data to train it. Okay, so this x. I used the x scaled, okay, and y to train it. Okay, now this model is built. The next one is an extra section. I want to see how the prediction changes when the k value changes. So for example, here we have built this model, right? We have built this classifier, the k nearest neighbor classifier. So we want to use this classifier to predict every dot on the every dot on the map. So we'll see, hey, if the x is here and y is here, what should be the result? And if the x is here, y is here, what should be the result? So we want to see the result of every dot on the map. Oh, yeah, if you have this map, okay. We have two variables here, and we have built this classifier. So we assume for each dot with the classifier, okay, we know the petal length and the width, and then it should return us, hey, whether this is the species 1 or species 0 or species 2, right? So we built this mesh grid, what they call mesh grid. So it means build x, y give it x values and y values. This x value is from 0 to 1, and get the each step is a 0.01. So this is the NumPy array, gives us the NumPy array from 0 to 1, and gives us each step is 0.01, and also the same with the y value. Okay, and now with this x value, y value, what we can do is to use the classifier to know, hey, which species it is, right? So the z value, the result we could get is to use the predictor, this prediction model, classifier model, to get the z value, which species it is. Okay, so now we get the x value, y value. For each x value, y value, we get the z value. We can build a map like here. So this one is to build the map. Okay, contour. It's build the map. So it gives its x value, y value, and for each xy, it gives the z value. The z value means whether it's 0 or 1 or 2, and no, this color, okay, 0, 1 or 2. So so for every dot, for each area of the map, it tells us hey, whether it's the species 0 or 1 or 2. Okay, so we can see from this map, it clearly classified, it clearly divided into 3 species. If the value is here, okay, this is a species of 0. And if it's here, okay, this is species 1. And it's a scatter plot of the original training data. So from this map, we can see this map is built on k equals 1. We got the k, when we built the model, we are based on only the closest neighbor. So what would be the problem with this map? We will look into this map. What do we find? Okay, it's roughly divided into 3 areas. However, these dots, these are outliers. Okay, outliers from this group, and it have affected this result. And the dots, it will be classified as this dot. It's fall into this area, but it will be classified into that area, right? That species. So these are, when k equals 1, these outliers largely affect the result. If we add another dot, if we add another blue dot here, then okay, this area will also be the gray area, right? The blue species. So when k equals 1, it's very sensitive, and it's largely influenced by the outliers. But if we k goes higher, 3 or 2 or 3, we see these blue dots, even they are blue, okay, this is not affected anymore. Even this blue dots is here in this area, it's identified still as the green species. So when the k value goes higher, this map goes smoother. The bottom, boundaries here go smoother. Right? So that's how the K value affects the result. So then the next question comes over how we can choose the optimal K. And we don't want it to go too smoother. And then maybe K equals 1 leads to overfitting, but if it's the K is too large, okay, if the K equals maybe like a 100 in the whole entire data, okay, then only classify to one species. That's not right. So what is the optimal K value? How to find the optimal K value? As we mentioned, that the K value should not be the multiple of the number of the classes. With two classes, it should not be even numbers. And 3 classes, it should not be the multiple of 3s. And the K value should not exceed the number of rows. Usually, the optimal K value is found at the square root of n. N is the total number of a sample, the number of rows. So, for example, if this data has 150 samples, 150 rows, and we would expect a K around 15, okay? But it's not always the case. So you don't have to go from K equals 1 to 150. Instead, you can go from 1 to maybe 20 or 30. That's enough. So simply, we want to find the optimal K. You have to go through all the K values and see, hey, which K value gives you returns you the highest accuracy score. Okay. So let's see. Let's go over and see which K value gives us the highest accuracy score. So with the knowledge we learned from previous lessons of how can we get the accuracy score, we build the classifier with the training data set, and then we use this model, prediction model on the testing set to get the accuracy score, right? So here I still use this model when K equals 1, and then I use this model I split the data into training and the testing data set, and then I use the training data to build this model. Classify K nearest K neighbors, classify when K equals 1. And then I use this model to predict the testing data to get the accuracy score. So this looks correct, and this gives us the number 0.83%. 83%. That's a quite good accuracy score. That's when the random state equals 60. So we mentioned what is the meaning of the random state? When the random state, if I change the random state, what does that mean? What does that mean?
The numbers between each data?
Yes, kind of. So we are divided the sample into 20% and 80%, right? So if the random state equals 1, or maybe it's getting this part, it's getting this part as the testing data. And when the random state changes, it changes to 20 or 60. Hey, maybe this it's getting this part as the testing data set, this part as the 20% for the testing data set. And when the random state changes to another number, okay, it's fetch this number, this part as the testing data, right? So when the random state changes, it gets a different set for the training and for the testing, which could result in the accuracy score is changed. So let's show the code. So for example, here, I change the state to 640. And the accuracy score changed. It was 0.83 and now it's 93. And if it changed to 20, or gives us 86. So which values would be the real value? When the random state changes, it gets the all different data, and it returns us the different accuracy score. How could we do that? And which one should we use? And see, you run different tests, all the same methods, but it gives you, because the data is different, so it gives you the different accuracy score. So ideally, what we need to do is to get all the numbers and get the mode or average number of the accuracy score. That could be more reliable, right? You know, it's get from the different data, different tests, different experiments. Okay, so yes, you can manually do that. I write a for loop, and then this random state goes from 0 to 50 or whatever number, and then get the accuracy score, and then get the mean. You can do that manually by yourself, and that. But there's a method here, new method here called cross validation. This method will help us to split the data into like into X times, and like what we did. Hey, first time it gets the scope of data for the testing, and the second time, if both is equal to 5, that means that it will have 5. We'll get 5 different training sets and testing sets. Okay, so the first time it gets this part for the testing, and second time it gets this part for the testing, and third time it gets this part for the testing, and then it gives returns the average score of all these 5 experiments. So this is another way for training and testing split. And usually we use it to compare the different models. Like we need to compare the decision tree with the logistic regression, or we want to compare the models with yes, so that's the limitation of training testing and we compare the models when the K value is different. We can use a cross validation. And here, for example, before that, we used the training testing split, right? And now when I build the model, okay, this is the model I built. Okay, do the model I built, k equals 1. And if I use this cross validation score, I only need to tell it the model I use. This model k nearest neighbor. This one k equals 1, right? Neighbor equals 1. Number of neighbor equals 1, and give it x the x data and y data, and tell it how many folds I need. In the picture I showed in the slide, the folds is 5, around 5 experiments. And when this here, if this CV equals 10, that means I run it 10 times, and it will divide the data into 10% testing and 90% training. Okay. And the score I want to get is the accuracy score. The accuracy. This scoring, it could be another score, precision, and recall, and precision recall, or F1. Okay, we'll talk about this at the next class about different scoring options. And then this gives us a CD score. This gives us a list of accuracy score when it runs over the 10 experiments. And then I can get the mean value of the scores from the 10 experiments. And this one, it's not 0.83, but it's also not 0.93. It's a number between this. That's the average number of the accuracy score we got from the experiment. Okay. We'll stop it here, and the next on Wednesday we'll run this we'll use this model to run over the k values to get the accuracy score, mean accuracy score when k goes from 1 to 20 or 30 or 150, but we don't have to go up to 150. And then to find the highest accuracy score. That's the optimal case. Okay. And the assignments for this week is open, and I think we already covered the majority, the most part for the assignments, and you can start working on it. Okay, we'll leave the rest of time